Telescope Public Lecture Series. It is my pleasure to be your host. I'm Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute. And when you came in, if you noticed them, we have pictures. We call these lithographs. This one is of a brand new one. This is the multi-wavelength Crab Nebula. What do we mean by multi-wavelength? Well, if you turn over, you can see that this individual image, the different colors, are composed of light from five different wavelengths, okay? From X-ray all the way to radio. And we have some explanatory text. You didn't grab one on the way in, grab one now or on your way out. Our talk tonight is the Plumes of Europa, ice, water, life? Which Susana thought would be a cool title to bring in an audience, and it is, all right? Next month, we will have gravitational wave astronomy, which is now a field, something we've been thinking about for decades, and it's now become a field. Our local expert, Andy Fruchter, will be talking about that. The month after that, Will Fisher is going to talk about one of my favorite places in the universe, star formation in the Orion Nebula. I'm really looking forward to hearing that. And then in July, we have one of these really long titles with the Milky Way's bulge, from a hypothesized blob to a remarkably detailed picture, talking about the center of our galaxy and the stars that orbit around it out in our center, called the bulge of our galaxy, okay? If you want to learn more about those or remind yourself of them, you can go to our webpage. If you go to your favorite search engine and type in Space Telescope or Hubble Public Talks, you'll find this page where we have the list of the upcoming lectures. Oops, there we go. Oh, I think my laser is going. All right. We have also on the left-hand side, we have the links for the webcasting, both the Space Telescope webcasting and our YouTube events. The live ones are active now because we're going live now. The archive ones go all the way back to 2014 on YouTube and 2005 on the STSCI webcast site. You can also sign up for our email list, which gets you about 2 emails a month reminding you of the lectures upcoming. That email is on here. Just sign up at the website. And those of you who can't handle going to a website can write it down on a piece of paper and hand it to me at the end of the lecture, and I can make sure you get on the email list. If you have comments or questions, you can send them to the email address publiclecture@stsci.edu. We have social media for both the Hubble Space Telescope, the Webb Space Telescope, and the Space Telescope Science Institute on Facebook, Twitter, YouTube, and Instagram. I myself am on Facebook, Google+, and Twitter, but don't expect a lot from me. I spend a lot of my time doing a lot of different astronomy things, and I don't have too much time to do social media. The observatory across the street will not be open, as you might guess from the weather outside. It's cloudy and a little bit rainy. But they also have open houses on Friday evenings. If you go to their website, md.spacegrant.org, you will find that page on the right-hand side, and in that box that says observatory status, each Friday evening by about like 5 or 6 p.m., they post whether or not they're going to be open for public observing. So yet again, we are unable to take you across the street after the lecture for that tonight, after the public lecture, but hopefully you can find it on one of the Friday nights. And now our news from the universe for April 2018. Our first story, unfortunately, is the James Webb Space Telescope had another launch delay. All right, and the NASA press, this is the James Webb Space Telescope. It is a 6.5 meter infrared space telescope it's really one of the most technically challenging things we've ever launched into space. Possibly the most technically challenging civilian thing we've ever launched into space. The NASA press release stated that the launch window is now targeted for approximately May 2020. Okay? Yes, we have to wait another year for it. All the observatory, but I pulled out specific quotes, all right? First of all the observatory's flight hardware is now complete, okay? So they've got the spacecraft element and they've got the telescope element. The stuff is complete and it's all together for the first time in the Northrop Grumman facility. Right? It is undergoing final integration and test phases that will require more time to ensure a successful mission. We all remember what happened with the Hubble Space Telescope, having a problem that needed to be fixed. JWST is going to be 1 million miles from Earth. It's not going to be a low Earth orbit like Hubble was. It cannot be fixed when it is out there. So it is extremely important to get it right and get it right the first time. As one of the JWST engineers says, we got to knock this out of the park, 1 million miles out of the park. All right, so yeah, we are taking the time to get it correct. And then the other question that people have is about the budget. NASA will provide a new cost estimate that may exceed the projected $8 billion development cost to complete the final phase of testing and prepare for launch, which means that they are currently evaluating what the delay will cost, and they will provide it to the American public when they have that. Okay? So it is still going to do the same great science. We're just going to have to wait a little bit longer for it. But it is, as I said, really important that we get it right the first time. So to me, it's worth the extra time, okay? Second story tonight, planetary construction dust. Now, this image is of a disk, or actually a ring around a star that's called HR 4796A, okay? And it came out in 1999. This is a Hubble image. And I was really excited when I saw this because I wasn't here at the time. I was up in New York City, and we were discussing the new discoveries in our own solar system, in particular the Kuiper Belt, okay? This new region of objects out beyond the orbit of Neptune, all right? And this is where Pluto lives, okay? Pluto is now the largest member of the Kuiper Belt. And so when you look in the lower right and you see that the diameter of Neptune's orbit is that, and this ring of material is just larger, it kind of got us excited because we were just discovering the Kuiper Belt in our own system, and here we were finding something of the same scale. However, this isn't a Kuiper Belt, okay? It's not made of ice. This is made of dust. And we wouldn't expect it to be a fully formed Kuiper Belt type thing because the star HR 4796A is only 8 million years old. But at 8 million years, that's the time scale on which giant planets form. Jupiters and such form on time scales of order 10 million years. So seeing a dust ring that's so tightly correlated here could indicate that a giant planet had formed in this system, has recently formed in this system. And that makes it exciting. Now, so we're going to take this image, we're going to shrink it and rotate it, okay? That's the exact same image, okay? And now we have a new image of HR 4796A that looks like that. Yeah, more sensitive, looking deeper, and seeing dust not in just a tight ring, but actually spread out across the system. See, 4796A is about 23 times more luminous than the sun. Right? So therefore, it has a lot more radiation pressure. And so while giant planets form on order 10 million years, planets like Earth form on timescales of about 100 million years. And in the process of building up terrestrial planets, you get a lot of things smashing together, all right? Planetesimal accretion. And that produces some dust, right? Planetary construction dust. And the radiation pressure from 4796A can actually blow some of that dust out of the system like this. All right? So the interpretation of this image is that some of this dust is coming from the possibly coming, or a reasonable hypothesis is that it's coming from the formation of terrestrial planets that's kicking up dust and then being pushed out by the radiation pressure of this large star, spreading it across the system. So that's kind of cool. And here is, by the way, all of the details of this. So 4796A is in that dark spot there. We block it out, of course, because if you have the star, you can't see the dust around it. You can see the ring. There's also, you notice, a bow shock, that curved line, because the star system is moving through medium, so you get a thing. And also in the lower right, there's a dark circle there. That is the companion star 4796b. All right. And actually, what I think is kind of cool, which we didn't mark, is in the lower left. That's a background galaxy. So we're looking at a star in our galaxy, but we're also looking at a background galaxy in the same image here. All right. So this may be the dust kicked up by the construction of planets in another solar system. Final story, a cosmology conundrum. About 100 years ago, a little less than 100 years ago, Edwin Hubble made this diagram. And on this diagram, he's plotting galaxy distance against galaxy redshift. And he found he got a straight line that galaxies that were further away had larger redshifts in a linear fashion. And this is the primary motivating evidence for the expanding universe. Right? That space is expanding, and therefore distant galaxies appear to be moving away faster in a linear fashion. However, the slope of it is the expansion rate of the universe, the current expansion rate of the universe, and we call that the Hubble constant. Unfortunately, he got the Hubble constant wrong because the way he was measuring distances depended on Cepheid variables, and he was using the wrong type of Cepheid variables, so he got it wrong by about a factor of 10. But eventually, we astronomers got it right. So this plot shows a date on the x-axis, and the value of h naught, which is this Hubble constant, starts out in the hundreds and then finally gets down to, when I was in graduate school in the late 80s, the values were between 50 and 100. So, we went from being a factor of 10 off to being down to a factor of 2. And hey, this is cosmology. A factor of 2 is good, right? I keep telling myself, I'm an astronomer. A factor of 2 is good enough for me, right? But that's still not good enough to do what we call precision cosmology. So when the Hubble Space Telescope came online, one of its key projects was measuring the Hubble constant by getting accurate distances to near galaxies so that we could really measure the Hubble constant carefully. It was an HST key project. In the year 2000, the data was released, and this is a graphic of the diagram showing that here are the points plotted, and plausible values were between 63 and 77. So that's great. We've gone from being a factor of 10 off to down to a factor of 2, down to 10%. Okay, we got a difference of 10%. But can we leave that alone? No, we're scientists. We really want to beat that down and beat that down. So what they have done with Hubble recently is they went back and remeasured the Cepheids in our galaxy, the calibration method, as well as doing other things. And we are able, in this new paper that just came out, get it down to a range of 72 to 75. Success! We finally have this Hubble constant measured. Except, in the meantime, we have developed other ways of estimating the Hubble constant. One of them depends upon measuring the cosmic microwave background. This is the COBE satellite, the first measurement of the cosmic microwave background, which then got refined with the WMAP satellite, and then got improved just still a little bit more with the Planck satellite. And this is measuring the temperature differences, which is basically the density differences in the early universe. And from that, what we really measure out of the cosmic microwave background is something we call the power spectrum, which is how much density is on different scales in the early universe. And from that, we can extrapolate through to the rest of the universe and start figuring out the expansion rate. In particular, the second peak of this power spectrum is sensitive to the Hubble value, the expansion rate of the universe, okay? And so its location and its magnitude gives us a good estimate of the Hubble constant. Doesn't give us a perfect estimate, but it gives us a good estimate. Combine that with two other ways of measuring things, one from supernova and one from something called baryon acoustic oscillations. It's labeled BAO. I'm not going to try and explain that in 30 seconds here. It doesn't work. But trust me, combining the three of them, the cosmic microwave background, baryon acoustic oscillations, and the supernovae, you can get another estimate of the Hubble constant independent of the Cepheid variables and all that. And it comes out to 65 to 69. Here's the problem. Both of these methods are tried and true. Both of these methods we believe, are estimating their errors well. All right, the local ones 72 to 75. The large scale ones 65 to 69. And the quote from Adam Rees, the head of the researcher, says, both results have been tested multiple ways, so barring a series of unrelated mistakes, it is increasingly likely that this is not a bug, but a feature of the universe. That our local estimates of the Hubble constant value, differ from our large scale estimates of the Hubble value. What do we do? Okay? Well, if you read the news about this, astronomers are baffled. No, we're not baffled, okay? We're intrigued, we're excited, because frankly, if we knew everything, we'd be out of a job. So this gives us something new. There's something new in the universe. It's either our problem, which it's unlikely, or there's some new feature in the universe. So of course we can come up with new ideas. And so some of the new ideas are perhaps there is an undiscovered subatomic particle, such as a neutrino with mass, that changes the measurements that we would get from one of these values. Basically, that would be on a large scale. Or maybe dark matter doesn't behave exactly the way we think it is. We think dark matter only behaves gravitationally. Maybe there's a little bit stronger interaction between dark matter and normal matter. Or the most popular one that you can think of today is, what about dark energy? We don't know much about dark energy. We've got a lot of ignorance there. Maybe some of that ignorance affects one of these measures, okay? So we have a lot of hypotheses and ideas on what might resolve this. But all I can really say is stay tuned because we have identified a discrepancy, right? And the process of science is we're going to hack at it, and we're going to hack at it, and we're going to hack at it till either we figure out what's wrong with our observations or we come up with a really good idea that can explain this discrepancy. And to me, that's part of the joy and excitement of science. When you find something that you can't explain, then you're just like, oh, we got to figure this out. Unfortunately, it'll take a decade or two to actually find out. So stay tuned and keep coming to the public lecture series. I'll make sure that I have it for you. All right? Okay, and that's our news from the universe. Our featured speaker tonight is Susana Deustua. She has been here for, 10 years? And she works in the INS division on the Hubble Instrument Wide Field Camera 3, or we just call it WIFC 3. I asked her for some interesting things about her, and she said that she fly fishes from her kayak. Combining kayaking and fly fishing together. And that once she did jump out of an airplane, even as well as having never been on the space shuttle. Okay? So here to tell us about Jupiter's moon, Europa, is Susana Deustua.
Thank you. And I think I'm number 1 or 3. Maybe I'm 3. Okay. All right, so we're going to talk a little bit about the water plumes. Ooh, what's happening here?
Oh, that was me.
Oh, that's you?
Sorry. It recalibrated after I disconnected, sorry.
Yeah, it's fine. We're patient. Somebody needs to sing the Jeopardy tune. Okay, so with any luck, I'll be able to tell you a little something about the plumes on Europa, water, ice, life, which is a little bit like our Baltimore winter this year. Let me see, which way does this go? As always. So this is the abstract that I put together. But more importantly is there are lots of people working on understanding what's going on with Europa in advance of perhaps actually sending a dedicated mission. And I was trying to play around to figure out whether this was Team A or Team B or the Roth team or the Sparks team, and I gave up on that because people go back and forth and people talk to each other. So I'm sure that I inadvertently might have left off some people, but I apologize if I did that. So more importantly is, as an observer, probably not tonight, but maybe when it's clear, if you go out look in the southeast, kind of find where the moon is, and you will see Jupiter. And so Jupiter is a planet, as you all know, that we've known since antiquity. When our ancestors first became Homo sapiens, I am sure they looked up and saw Jupiter and named it something. And 400 years ago, in 1609, Galileo, as we know, I wouldn't say he invented the telescope, but he was one of the first to put it together. And incidentally, he was very ill. He had like the flu or something when he was putting together the telescope. I guess he kept him from being too sick. And later, he turned that telescope, and he was the first to point at a celestial object, and in his case, it was Jupiter. And what he saw over a period of time were a series of moons or objects or little stars that were revolving or moving around Jupiter. And this is just a blow up of that letter that I showed, which is a letter he wrote to the Doge of Venice in 1610. And in that letter, he is describing his observations. So 1609, first observations of Europa. And if I can do this, I will start the movie, because this is kind of cute. I love the internet. This is a movie put together by a gentleman named, I think, somebody Wright. He has a website. He's a computer scientist by profession. And what he did is he took all of the observations that Galileo had recorded, and he juxtaposed those on the ephemeris. And so what you see now is the beautiful pictures on the top, and then Galileo's observations on the bottom. This is just sort of a fun little thing, and it'll go through so sort of the modern and the ancient. Okay, so let's just put this in context a little bit. When we talk about the moons, it's natural to think of it as being like our moon. So here's our moon here. This is Europa, and it's about the same size. Over here, so that's kind of comforting. Moons can be the same size as our moon. This is Callisto, Ganymede, Europa, and Io, or Io, the four Galilean moons, although Galileo called them the Medici moons, as you remember, because the Medici were his patrons. It's always good to keep your patrons happy. Anyway, so here's Europa. It is not the largest of Jupiter's moons, but it is certainly one of the most interesting, along with Io. And Io is known to have volcanic activity. And just for fun and scale, here's one of the bands on Jupiter. So you get the sense that these are actually relatively small, and Jupiter is very, very big. So we'll skip forward a few hundred years to the Voyager missions. And the Voyager, I think, are the most successful missions, in my view, that NASA has put together. They have been going through the solar system for over 30, approaching 40 years, returning good data ever since. And this was one of the first images that we had, close-up images that we had of Jupiter and its moons. This over here is Io, and this is Europa down here across. And these little dots are just some fiducial marks on the imaging system of Voyager. About 20 years later, there was another mission, this time called the Galileo mission, which also went to Jupiter. And what I think is remarkable, and a lot of people have as well, is that we see Europa. This was taken about, I don't know, almost 60,000 miles away. Is that Europa is relatively smooth. It doesn't have big, huge craters. It doesn't have big, huge mountains. And it's got all these little striations all over it and some dark spots. So it's a very interesting moon. It's an interesting object in and of itself. And this is a beautiful image that got reprocessed in the imaging department by somebody, so to highlight the striations and sort of false color images. And what you see is that these look like cracks in the ice, fissures in the ice, which tells you something about what is going on on the moon. And this is a blow-up also from the Galileo spacecraft, where you can see these cracks and fissures and apparently some deposits of material, because it's not all white and icy. So this points to, and there have been a lot of papers and people got really busy and said this looks a lot like cracking of ice, and maybe it looks a little bit like plate tectonics like we have on Earth. The continental crusts and are shifting around and subducting and separating. In this case, this is on the icy surface, so it's a very, very intriguing. But in addition, one of the things that the Galileo spacecraft had with it was a magnetometer. So it was measuring the magnetic field around Jupiter. And an interesting thing is that if you have another source of electromagnetism, it's sort of like having two magnets. If you try to put the two south poles together, you get a little deflection. Have you ever tried that when you were kids? So you'd see something similar if you had another source nearby. You would see a little deflection in the magnetic field. So when Europa was passing through Jupiter's magnetic field, the magnetometer detected a deflection. And that deflection was consistent with another conductive or an inductive body, and it probably had to be something like slushy, salty water, because it had to be something that was globally connected. You couldn't just have one little pond. It had to be all around. And about the only thing people could think of at the time was some slushy, icy material, which of course makes things really, really interesting, because now we have ice on this planet and potentially also water. And so this is a sort of a model of what this might look like. Here's the water down here, some kind of a thick, warm ice shelf, and here you can see the cracks on the top subducting, just like they would on Earth if you had plate tectonics. And where there are little soft spots, you might see sort of cryo lava. So instead of being molten lava, it would be molten water, otherwise known as liquid water. And this would be something that would build up over time. And the other clue to this is that was because the surface of Europa is so smooth, it doesn't have a lot of cratering, which also indicates it's a young surface. And the only way you get a young surface is if you have some regeneration of material that covers the cracks in the craters. So this is all pretty fascinating, and people got really intrigued. But this wasn't really enough to answer the question, because you could still imagine having a rocky core in the planet, ice, warm ice, and then cold ice on the surface. Or maybe you had a rocky interior, and then a water layer down here, and then ice. And this was something in play. If you have a lot of ice, it's probably not so interesting, or maybe it is. But if you have water, now you start thinking, could you possibly have something really interesting going on if you have water? And the answer, of course, and what we're working up to is if you have water, then you have life, or you have the possibility of life. But the one question is, Europa is far away. It's very far from the sun. And you have this icy cover. So how would you get heating of the material in order to have a liquid water ocean? And so one potential answer, and this is probably the right one, is something called tidal heating. And what that does is as Europa goes around Jupiter, it's not in a perfectly circular orbit, so you have gravitational forces acting on the moon itself, sort of pushing and pulling it. You can think of it as either, when you bend a spoon, you get a little heat, or you're stretching a rubber band and you feel it, it gets a little hot. So it's sort of like friction. And that is probably the source of the heat that keeps the water liquid. Then the Galileo mission, I think, has given planetary astronomers a lot to work on. But I think it's been about 30 years, and we're about due for, NASA guys, if you hear me, we're about due for another mission. So this is a particular region on Europa, and you can see the striations there. This region is highlighted, and this is now work that comes from Brittany Schmidt, who's been working on this on Europa since she was, I think, in grad school. And what this shows is a region that it looks very chaotic. It looks sort of crumply, like something happened there. It's not a crater. It's like a typical crater. It has a little cone shape, and you see the material on the side. But this seems to indicate that there might have been a region on the planet, on the moon, that might be the source of some kind of flow of material. A crack in the ice raises the material. And so she developed a model that seemed to indicate that you had to have some kind of water driving this type of feature, liquid. And Galileo got to the rescue again. And one of the John Spencer studied the thermal mapping of Europa, and just because you want to know what's going on, what's the temperature on the surface? Is it all the same temperature all around? Is there variation in the temperature? Is it hot, cold? Is it like the Earth where the poles are colder, etc.? And so he did this heat map, if you will. It measured the temperature in various locations. This is sort of at the South Pole. This is sort of hot. You have regions where you go from warm, relatively warm, to cold, and these are degrees, I think, Kelvin. So this also tells us that it's not a solidly single temperature situation, which just adds to the intrigue. So this is a bit of an artist's conception. I think that between Galileo and Voyager and a lot of heavy lifting by planetary scientists, we sort of came up with the idea that we had a salty liquid ocean, and that potentially you could have some kind of geyser activity if you had liquid water depositing. Here's sort of one of those little chaos terrains like the one I showed you earlier, pool of water underneath. This is probably some thin layer of ice, about 100 kilometers thick. You get a little water pooling up, and it comes up, and maybe you could see geysers. And so this seems to indicate all that. It seems to indicate that this is really the right idea, the right model for Europa. So you do have a liquid ocean, a salty liquid water ocean underneath ice. And now things get really interesting. Because this is not Europa. This is Enceladus, which is a moon of Saturn. And Cassini, which did not go up 40 years ago, more recently than that, took a picture of Enceladus and noticed that there was water vapor on the South Pole. So if Cassini has this, what about Europa? So if Europa also has plumes of water vapor, then maybe we can learn something about its ocean without necessarily having to go and send a mission and do ice cores and drill down 100 kilometers into the ice. So this is where Hubble comes in. And this is work that started roughly around 2010. So this is Lorenz Roth et al. Came up with one technique, and it's called spectral imaging. And I wasn't, which is not the same thing as direct imaging. So we think of a spectrum as white light coming through a prism or a dispersing piece of glass and then getting broken up into its constituent colors. We've all seen that, or a drop of water, or your hose, or the rainbows, they all work the same way. And if you remember from your physics class, whether it was high school or college or graduate school, or maybe even last week when you were analyzing some data, typically when we do spectroscopy, we talk about having a slit, and then you have the disperser. In this case, it's a prism, and this is just a model. It gets sent off, collimated, and what you see then is a bunch of lines, either absorption lines in this case, or emission lines. And that's the normal way of doing things. But in actuality, what these little lines are actually an image of the slit. So what happens if you take a moon and you use your traditional small slit? Well, you can't see the whole moon, but if you make the slit bigger, and fortunately, one of Hubble's instruments, the Space Telescope imaging spectrograph, has a slit that's about 2 arc seconds wide, and Europa extends an angle of about 1 and a bit. So you open up the slit, and you go through your same system. So this is now standing in for the entire set of optics that are complicated. And what you get is an image that's no longer those straight lines, but rather an image of the source, because you've made the slit large enough. And then the idea then is that we know that if there is a plume of water, when water hits the atmosphere, water's hydrogen, H2O, 2 hydrogens and an oxygen, when it reaches the atmosphere, it will dissociate, or it exits the atmosphere, it will dissociate, break apart into hydrogen and oxygen. So the logical thing to do would then be to look for the dissociation products of water, which are hydrogen and oxygen. And in the ultraviolet, there are 2 lines of hydrogen and oxygen. And this is what Lorenz Roth and his team took advantage of. And so in 1999, this is the series of images. This is the hydrogen lines, these are the oxygen lines. In 2012, they took another series of images. But in December of 2012, when they saw those images, what they noticed is that unlike the earlier images, there was a little excess of both hydrogen and oxygen down here. And that indicates that there was a plume. And they wrote a paper in Science, which is here, it came out in 2014. There were subsequent observations, almost 17 detections or orbits, and there were no additional plumes discovered. So now, just like with the presentation earlier, is this the data? Did we, everybody thinks, did we screw something up? What's going on that we don't see it again? You get really panicky. You think you've done something wrong in the analysis, and you go back, you do the reanalysis, and it's like, no, this was correct. But because they didn't see the plumes again, there was already hints that Europa could not be like Enceladus. Enceladus is very regular cryovolcanism, if you will. So if you wanted to take a pretty picture and put it together, so this is the location of the plumes, and then here is Europa. Okay. The other thing about science is that you like people to repeat your experiment in some other way so that you have some confidence of what you're doing. So the second method was to actually use direct imaging. So no longer using spectrograph, but just direct imaging, just like you do with your camera. Take a picture of somebody or the tree or the pussycats. Okay, that's direct imaging. In this case, there had been an example. In 2000, John Spencer had looked at Io in the ultraviolet. So this is Io, and this is Jupiter in the background. And you'll see there's a little plume here. Remember, Io really is volcanic. And so the idea was that, look, if this worked for Io, where you can have Jupiter effectively backlight, so you're seeing Jupiter in the backlighting the atmosphere of the moon, the tenuous atmosphere. If there's anything going on, you should be able to detect it. So the second idea then was to do direct imaging in the far ultraviolet, around 150, 160 nanometers. This is a region that is, of course, not accessible from the ground. And we took images for almost 3 years, well, 2 years. And we had 12 images of Europa in transit. And what we were doing then was measuring the atmosphere, not necessarily looking for jets, but just changes in the thickness or the opacity of the atmosphere. And we also, just to double check, had images taken out of transit just in case it had something to do with being in front of Jupiter. And the analysis of this data is pretty straightforward. Here's the real image of Europa. And this is Jupiter in the background. And what you want to make sure is that when you do the subtraction or the analysis of the image, that you're not doing anything crazy. So the standard thing to do is to say, assume a circle, and you assume some kind of illumination pattern. You figure out what Jupiter looks like in the background. You make a model, and then you subtract the model. Well, you actually also have to add, the effects of the instrument on your model. So you're making a fake image. So here's the fake image, and here's the real image. And they look okay. They look plausible. This is one that doesn't have plumes, and this one in the model doesn't have it either. So this tells you something about gives you some confidence that your method is actually going to work. And then just for fun, here are just what these images look like. Here, because Jupiter moves, now here's the fun part of doing planetary science, which I hadn't quite appreciated until I started doing it myself, is that everything moves. Jupiter moves, Europa moves, the satellite moves. So everything has to somehow work together, and you have to decide whether you're going to track on the moon or Jupiter or both. So this is what it looks like if you assume that Jupiter isn't moving, and then here, if you assume Europa isn't moving. So here's Europa, and here's its shadow, and there's a lovely aurora. And then I have to show this because this is kind of fun. If you put all the images together and you derotate everything, then you can make fun images that show you, here's Europa, here's Io, here's the gray-red spot, and obviously it's a partial image because we're not imaging the whole of Jupiter's face. So that's kind of fun. And the reason we could do this is that one advantage of the STIS spectrograph or imaging system is that you can actually take observations at what's called time tags. So the separation, each exposure is 0.125 seconds, and you just can keep doing that. So every 10th of a second, you have a new image, which is one of the things that lets you make these lovely movies. But it also helps if you're trying to look for features. And then you can also play some more with these images. And this was made by Sean Lockwood, who's also on the staff here. And from the same data, because the movies are kind of fun. What's the point of doing this if you can't have fun? So here you see the aurora, which is kind of fun. It changes with time. And here is Europa. So this is, not enhanced at all. And then if you really want to see what, again, unenhanced. So we'll just skip right past this. Because the thing that's interesting is that what we're looking for is 3,000 kilometers, and this is Europa's north. And then just to show you, because you got to show the data. I've talked a lot about it. I've shown some pretty movies, but I haven't shown you the data, which you should always ask. Where's the data? So these are the 10 of the 12 observations that we took, and 1, 2, 3, 4, 5, actually 1, 2, and they're given in time. So we started in December of 2013 through March of 2015, and we did that whole careful analysis, subtracting out the model, making sure, and you'll notice, if you look carefully, that there are only 3 of these images that show something different. 3 of these are not like the others. And those are the plumes. Maybe. Okay, and this is just a close-up. And what these are done here is you subtract the model out, and again, you see the enhancement. So I know that we had a lot of discussion because now we saw 3, we didn't see them sequentially, and then we looked at the Roth paper, and it looked like they were in the same location. And in addition, we actually found a plume in a different location. Remember, the other ones were down here. In March of 2017, we actually found something, a little poochy thing over here that repeated again there. So that would be a second plume. That's really cool. And this is just more of the images. And then just to prove that we weren't kidding ourselves, we added, subtracted, and convinced ourselves that that was right. So where are these plumes found? So the ones that the direct method, the direct imaging method found, right just north of the South Pole, and then right here near this crater called Puil. And we saw it twice. So the plume at Puil repeated. We saw that twice. This one we've only seen once. And this is the location of the plume as seen with the spectroscopic method. So we have 1, 2, 3 plumes, if you count them. And one of the things that's really neat, you've seen this image before because I showed it to you earlier, is that here's Puil. This region here is like 2 degrees warmer than the surrounding region, and that's coincident with that repeating plume. So the question we're asking is, are they related? Is it possible that you could have a slight warming of the ice? Would that be enough to allow some liquid water to come through to sort of break through? It's intriguing. We don't know, but it's a possibility. And so this might be what that looks like, that plume, rising 125 miles above the surface. And of course, there's Jupiter in the background. So looks like there's probably water on Europa. And the observations continue. We didn't just stop in 2017. Both groups as amorphous as they are continuing their observations using different techniques and different analysis methods. So this is from our most recent 2017-2018 data taken with the Hubble Space Telescope. And again, it's really kind of fun to see them move around. This is Ganymede up here, by the way. That isn't just a splotch. And you can see Europa over there, and then you can see the lovely, I love the aurorae on the poles of Jupiter. Okay, so that's fun. There's a close-up of Ganymede. So if you have water, we have ice, we think we have water. The good thing is that both groups got the same value when you do all your calculations. Not only were the plumes coincident, so that the Sparks team and the Roth found one plume coincident or near each other, and we saw one that repeated. But we also determined the amount of water based on the images, that the amount of water was about the same. So you don't get the same numbers unless you're more or less on the right track. So now we have the ingredients for life. So what do you need? You need atoms, you need molecules, you need the most important molecule of all, H2O, and you need energy. Now on Earth, the energy that life, as we know it, uses, it comes from the sun, plants, the animals that eat the plants, algae, slime mold, bed bugs, etc. All derive the energy required to synthesize these elements into the amino acids. There's a long biochemistry chain that happens. Sometimes on Earth, we have hydrothermal vents. Go to the bottom of the ocean, there's volcanic activity, and that heats up the water, and you get these hydrothermal vents, and we found and people have looked and found life, bacteria and so forth, living there. And this is a model sort of indicating the tidal heating. So if you don't have direct energy from the sun, and you may or may not have hydrothermal vents, you still need a source of energy in order to be able to do the chemistry that allows the biology to happen. And in Europa, this would be due to the tidal heating. So there is an energy source. And many years of people studying evolution. So life on Earth is divided into 3 clouds. Okay, 3 different groups. We have what are called the bacteria. Some of them we don't like. These are generally single-cell animals. We have what's called the archaea, and those are generally those extremophiles, those organisms that like to live where it's super salty, super acidic, super alkaline, super hot, super cold, super high pressure, super low pressure. And then we have the eukarya, and that's everything else. This is slime molds, bed bugs, people, cats, dogs, your neighbor. And I just put down this last common ancestor because it's kind of cool to see the quote-unquote tree of life. And this one gets very messy, and so does this one. So I just put clouds. But the main difference between the left side and the right side is the kind of cell that makes up the different kinds of life. And I have a question mark for the viruses because nobody really knows where they fit in. So these guys have one particular kind of cell. It's very simple, and these organisms over here are all single-cell organisms. Whereas, as we know, on this side, on this side, we have multicellular organisms as well as single-cellular organisms. And the cells are more complicated. How, things like that, then you start getting into things like how is the information for replication or reproduction carried in, and the cells have different structures that do that. I think on this side, the eukaryotes over here on the right. As you can see, these are real electronic scanning electron images of these critters. So this cell here's the nucleus, this is where the DNA lives. All the genetic information, and you see they have all these structures, the mitochondria. You've heard of doing like mitochondrial DNA analyses to see where people came from. That's what they're looking for, is the DNA that's in the mitochondria. You have the plasma, you have a whole bunch of structures, and this is where all the biochemistry happens. That is life. Whereas on this side, these are the prokaryotes, whether they're bacteria or archaea, they're really simple. Here's something that's called the nucleode, and all the DNA is there, and then you can see there's just a couple of structures in there. So they're very simple. And of course, as we know from everything that's the eukarya, we have plants, so they have solid cells. So the cells on this side can be differentiated and have specific purposes. So here we go. So life on Earth, the bacteria, this is actually a picture of E. coli. I had to find one that was icky. This is a methanophilic animal. It loves methane and it lives where there's a lot of methane. This is a single-cell organism, it's probably an algae, and then here's the great white whale. So this side we have a lot of diversity. Here we have a lot of diversity, but they're unicellular. So then let's ask the question of what would life on Europa look like? And it is probably not going to be what we think of life. It is probably going to be something called extremophiles. Now there are some bacteria that are extremophiles, and some of these guys are extremophiles. So these are sort of the temperature ranges, -18 to 15 degrees Celsius, 60 to 121 degrees Celsius. Remember, water at sea level boils at 100 degrees Celsius. Pressure is like from 1/100th of an atmosphere to 1,300 times on Earth's atmosphere. So obviously this would be at the bottom of the ocean in the deep trenches. This might be sort of on the top of a mountain. They can live in places that are up to 38% salt. And just as an example, seawater is only 3% salt. Whoops. Some of them like to be really acid. Sulfuric acid is about 2. And then we have very basic, 8 to 12. Most of us like 7. And then some of them can also withstand a lot of ionizing radiation. So that would be X-rays, gamma rays, ultraviolet, even some of the products from radioactive decay. And they also seem to be very resistant. There are some that are very resistant to cosmic rays. And you have to remember that, for example, when people are talking about traveling from Earth to Mars or to any of the other planets, humans, one of the things that people worry about in transporting humans across space is the effect of cosmic rays. These are very high energy charged particles, and they damage cells and can lead to things like cancer and disease. So that is always a concern on, say, interplanetary travel for humans, is how to protect living creatures from cosmic rays. But it turns out there are some of these extremophiles that are happy to deal with it. So here I have 2 images. Here's another bacterium. This is actually a salt-loving bacterium. And this is a giant squid. And Europa probably doesn't have the giant squid. So I think we're going to see the bacteria and the archaea living in Europa. And where would they be found? Well, here's a scale. So here's somebody's view is that there is probably a hypothermal vent or hypothermal vents in the deep ocean of Europa that heats up the water, and then sets up a convection which allows I want to call it the nutritives, but the basic elements that are used for biochemistry as we know it, carbon, oxygen, phosphorus, etc. And then life, bacteria or archaea, would end up living at the bottom in sheets, perhaps, or upside down mounds on the bottom of the ice. Some of them might actually, if there was soft ice or a vent, some of these living creatures might actually end up working their way up to the surface, much the same way that rocks and meteorites in the South Pole work their way up to the surface. They just get dredged up, or I forget what the actual word is for it. Well, dredged up by the physical forces. And from the surface of Europa, you can get some of the oxides, molecules with oxygen in them might also make their way down sort of in the same way through fissures in the ice. And so it is highly likely that you would end up with life on Europa living on the ice shelves. And so the next question is, what comes next? And NASA has been looking at a concept called the Europa Clipper, which is a mission to go to Europa and possibly fly through a plume and see if any of these, if there was any, what's in the plumes? Could there be some biological material in the plumes? Desiccated, of course, but would they be there? Would it be possible to send some type of a probe that would land on the surface of Europa and perhaps be able to either cozy up to one of those little chaotic pieces of terrain or a soft spot or near one of these plumes and actually do some contact excavation? And I think that would be really cool. So, but this is something that is being studied very actively, because this would be perhaps Europa is after Earth, where we know there's life, is the next most likely location suitable for liquid carbon life as we know it in the solar system. And that would be super exciting, I think, if something went there and we discovered there was life there. I think it would also be super interesting if we didn't find life there, Because then you could ask the question, was there ever life? How would you know? Would you be able to find fossils? On Earth, we do find, well, the people who look for them have found fossilized bacteria, so it's possible. One could find telltale signs of past life. Or perhaps life hasn't actually started yet. These are all possibilities. So I'm just going to end here with one last slide. I don't know if it was Galileo's dream to go to Europa or not 400 years ago, but I think he would certainly be interested and would probably be a promoter of exploring the icy moons. This also turns out to be a pretty good book. And so I will stop here. Guess we have time for questions?
We have plenty of time for questions, including a few that appear that they're going to come from online as well. So.
Uh-oh.
Yes.
Hubble be turned back to Earth to look at phenomena like you have described on Europa and actually know what's going on Earth?
Okay, so I have to repeat the question for the online audience. Can the Hubble be turned back on Earth to look for the same sort of things we might be looking for on Europa?
The short answer is no. Hubble is actually designed to avoid looking down on Earth for logical reasons. But there are other satellites whose missions are to look down on Earth. So there is a whole suite of Earth-observing satellites. Now, I don't know the details of whether they would have all of the sensing equipment to be able to look for life, but that is one of the few things Hubble cannot do, is turn around and look at Earth.
Over here.
So you mentioned that a lot of the heat energy on Europa comes from this gravitational deformation over time. Does that periodicity co-occur with the plumes that we see, like
That's actually some
mechanism?
Okay, so the question is, does the effect of the tidal forcing of the tidal heating of Europa coincide with where you see the plumes? And in fact, I just read a paper on that, and I think the answer is no. That is what, in fact, Enceladus is locked, but Europa is not. So I think that's one of the other pieces of evidence that we're not looking at exactly the same thing.
In the green sweater there? Yes, you.
When the bottom, I think you said it was 100 degrees Celsius, when it comes through the ice, what temperature would it be outside of that?
It would be like 94 degrees Kelvin.
Oh, not too much different?
No, because you only have a little bit of 100 degrees Celsius as it comes out, and then it'll cool. And remember, the ice is 100 kilometers thick.
Okay.
So the surface of Europa is quite cold.
Okay, we'll go back over here.
What is the movement of temperatures on Europa? I mean, we're talking about a very fluid state. Is there a fluid thing of the temperatures that are experienced on Europa?
So the question is the temperature on the surface of Europa fluid? And the answer is, I'm not sure. Because sometimes Europa is facing the sun, so it's going to have a little more insulation. I think overall, if we go back and look at those beautiful images, let's go back and look at the numbers. Let's do the numbers. So what you see here is that you see it's roughly about 80 to 90 degrees Kelvin, with a little bit, maybe getting up to 130. So I don't know if that means it's constantly changing, but I think it's pretty constrained. Obviously, when it's facing the sun, it's going to be a little hotter.
Right, yeah, your image on the right is, it says marked as daytime, and that
Yeah,
has
this
your
is daytime.
130.
And this is nighttime here. So there's probably a 30-degree change between the daytime and the nighttime. But I don't know if that means fluid.
Okay, so over here in the black t-shirt?
Yeah, so
Black
very
shirt?
generally then, what is the theory behind why there's only a certain area where we're seeing plumes as opposed to the rest of the area? If it's not due to the periodicity of the time
Right.
courses, what is the general theory?
So the question is, what is our understanding of why we only see the plumes in one location?
Yeah.
Good question. That's what we're trying to understand, actually.
And isn't that what, one of the things Europa Clipper would be able to understand?
Europa Clipper will be able to probe a little better. So there was a question earlier, and so doing the comparison between Europa and, say, some of the other moons, not quite seeing a direct analog, particularly with Enceladus. So it is an open question. And yes, having a mission actually go there and get really close and personal would be a wonderful thing.
Right, so there was a question online, let me just interrupt with that was sort of related to the Europa Clipper. They were wondering all right, so they recognize that, yes, you have to go survey. What would be the timescale for a lander mission is what they were asking.
You mean, like, when would that happen?
Yes, if Europa Clipper went up next decade, would there be? 'Cause several people online were very concerned that we need to be able to measure the water on Europa before they die.
Yeah, how old are they, and where do they live? I think it's likely within my lifetime,
Okay.
and I would hope in 20 years.
All right, so we'll just call it decades, okay?
Yeah, it's not going to happen next decade, but I think in the 30s would be a reason, possibly.
Down here.
So along those lines, as you're doing this investigation with your teams, is there the beginning of a communication with NASA planetary probe designers?
Oh yeah. There are
to open that up?
There are people on the team, not me, because I'm sort of a, lower level type player in this. But there are people there who are very active in talking to NASA about that.
Okay, here. That's you.
Sorry. Cassini flew through the plumes of Enceladus
Mm-hmm.
and measured some of the chemistry. How similar do you suspect the chemistry is going to be in life in the plumes of Europa?
Okay, so the question is, Cassini flew through the plumes of Enceladus and made some measurements of the chemistry. And so the question is, if you went through the plumes of Europa, what would that chemistry look like? I'm not actually sure I know the answer to that. I think it would depend on, well, you'd want to see some evidence, for example, like hydrogen compounds, sulfate compounds, maybe iron compounds. But I don't know the quantity offhand.
Would it matter that much that Enceladus is sort of a medium-sized moon, whereas Europa is a large moon? Europa's
Probably.
one of the
Probably.
7 large moons of the
Yeah,
solar
it is,
system.
it is.
And Enceladus is just one of the many medium-sized moons. So that's one of the major differences when I think of those two.
Right, and then in addition, the cool thing would be to find the bacteria.
All right, in the back up there.
If we knew that there was life on Europa, what would the implication be because there's life in the solar system, so, big deal, it's in the solar system. What's the implication for the universe?
I think it certainly opens up the definition of the habitable zone. So, so the question is, what is the implication? If life were found on Europa, what is the implication for life in the universe in general? So I'm going to back that up a little bit, which is that on Earth, wherever there is the possibility of life, there is life. So life is very tenacious. And that just take the, the basic definition of life, organic, an organism that can replicate and eats and poops. That's the basic definition of life. It maybe moves around a little bit. If there's life on Europa that tells you that you don't need to have direct starlight, whether it's sunlight or that, to provide the energy, and that's a little different because that's one of the difficulties is on Earth is knowing exactly when you're no longer dependent on sunlight. So if you're in the bottom of the ocean in the trenches, the hydrothermal vents and so forth, you're not getting a lot of sunlight down there at all. So that's a possibility. So then when people talk about looking for extraterrestrial planets and looking for evidence of life, there's a whole discussion of what's considered the habitable zone. Or some people call it the Goldilocks. You may have heard of it as the Goldilocks effect, which is where now you're looking at, but there you're looking at things like what could be an Earth, as we know Earth. If there's life on Europa, what that tells us, I think, is that the definition of a habitable zone, you can have one for planets, but you might also need to sort of think about all the conditions that are necessary, going back to the basics of energy and chemistry that are necessary. So I think it opens it up. I think it also makes it much harder if you're looking for moons around Jupiters and extraterrestrial planets, and exoplanets, it's a more difficult to find. But I think it would imply that it's probably more prevalent. This is now my personal opinion. It's more prevalent than we might otherwise have expected. It's a long-winded answer to a short question.
All right, other questions? Peter?
Could there be another source of heat for Europa, like radioactivity from the core or anything like that?
So the question is, could there be another source of heat, like radioactivity from the core? Probably, but let's say these formed 4.5 billion years ago, 4 billion years ago. I don't think it would be enough. I think you would definitely need the tidal heating to keep that ocean liquid.
And how much water do you think is on Europa compared to the amount of water on Earth, say?
Some of the numbers I've seen, like 6 to 10 times the amount of water on Earth. It's a huge amount of water.
Okay, was there a question in the back there? Other questions? Anne?
So when you showed the characteristics that life would have to have if it lived on Europa, I kept thinking about something like tardigrades. So is it possible that there could be something more than a single-celled creature on Europa? Tardigrades are so tough and so tenacious.
Yeah. No, I think it's possible. It's probably less likely. Yes, tardigrades are very tenacious and they are very tough. They're really hard to do away with. I mean, and they're used in school labs all the time because of that. So they do have a chance. A tardigrade. Do you want to? And what's it?
Tardigrade is also called a water bear. They're these little, almost microscopic creatures that are found in pools of water and lots of places on Earth, and they can survive cosmic radiation. They've been used on the space shuttle. They can desiccate to like 1% of the water in their bodies and then regenerate in water and all sorts of other things. They're just really tough creatures.
But they are multicellular.
They're multicellular, yeah. They look like little manatees with 6 legs.
Yeah.
Do they grow?
Yeah.
Yeah.
Yeah, if you don't know about tardigrades, you might want to look them up.
Very cool.
My son at one of the science centers we went to spent about half an hour reading about the tardigrades, and it just was
Yeah, and
really cool.
Tardigrades are used for in a lot of astrobiology labs when they teach astrobiology, because it's one of those life forms that is very tough, and you can subject it to all sorts of conditions.
Where did they come from?
Yeah, Earth, everywhere. No, they're everywhere.
Okay, questions? You've had one more. I just want to see if there's any others before. Okay, back to you.
This, in general, with the moons of Jupiter, does the fact that Jupiter is a gaseous planet and therefore less dense than, say, a completely solid planet, does that affect the physical relationship, so to speak, the gravitational relationship between Jupiter and its moons, differently than, say, the Earth and its moon, because it's less dense in general?
So the question is, the fact that Jupiter is a gaseous planet,
Yeah.
does that affect the gravitational relationship between the planet and its moons?
Yeah.
Because of the density?
Yeah.
Are
there any weird quotes?
Yes, well, it's yes and no. Because if it's just gravity, then mass is more important than the density, so it's the total mass. But the fact that it has an atmosphere and has a magnetic field, so you start seeing interactions of the magnetic field of Jupiter with its moons, plus the aurora, which are, it's a chemical not a chemical, it's a physical reaction. So you're getting particles thrown into the magnetic field, so that will affect. So you can get sputtering, for example, on the surface of the moons. That's when material gets bombarded and then gets sort of scraped off. So the answer is yes to both.
Okay, Herman, okay, you can come in. One last question.
Is there something about Jupiter's magnetism or Jupiter's gravity eating the core of Europa?
I don't think so, no.
All right, so thank you all for coming. Next month, May 1st, gravitational wave astronomy with Andy Fruchter. Let's give Susana one more big hand. See how many.